Now we're going to discuss toroids in chapter 29, section 4. As usual, we will start with our Ampere's law. So mu naught b dot with ds, that's the integral we have. It's enclosed path, which is the Amperian loop. You can see it on the figure. And this is equal to mu naught times I enclosed as usual. And we are going to kind of solve simultaneously as we've done before. So we have b times ds cosine theta. That's equal to mu naught. And if you think about the I enclosed, so the orange circle is our Amperian loop, and it is enclosing the loops, but they're like each loop is carrying a current I, as you can see it here, and it is enclosing all the turns. So the enclosed current will be the current that is passing through one loop and times number of turns on the toroid, right? So this is the number of turns. So it's a little different than the solenoid. We needed to use little n for solenoid because our Amperian loop did not cover all the turns, current carrying wires, and here it does, so it's easier. Okay, and in terms of b dot ds, you can see the magnetic field direction can be the ds direction can be set to the same as magnetic field direction, so you can take this to be 1, theta being 0. So what we have then, we have b is uniform, right? We can take that out. ds becomes the, as usual, the circumference of that loop, Amperian loop. And here we have mu naught I n. So when you write this for the magnetic field, and I'm going to write it, it's the toroid, it is mu naught I n divided by 2 pi r. Again, mu naught is just a constant. We already know mu naught is equal to 4 pi times 10 to the negative 7 Tesla meters per m. And the current carrying wire, so there are several loops, but each loop is carrying the same current, that is I, and capital N is number of turns. Again, it's like depending on how many turns do you have, and 2 pi is just a constant, and r is the where we are measuring the B field. We are measuring the B field on the Amperian loop. It's inside the toroid, and as you can see from the equation here, this magnetic field depends on 1 over r. That would mean if you go closer to the inner surface, so you can see that the green B field right here, then the B field is going to be stronger because r is getting smaller, B is getting greater, and when you go towards the outer end of the toroid, but you're still inside the toroid, and that will mean B field is getting weaker. Okay, so toroid is like a donut shape, right? And it's like a solenoid, but then you put the two ends together to make that donut shape. And again, in these cases, we are in both toroid and solenoid, we are thinking about the magnetic field inside the object. Okay, so that is the toroid, and we are going to do some practices. We have an example to do. It's not very challenging really, other than using like the equation, knowing the proper equation. And you do have an example of square toroid. So instead of this circular shape here, so you can see that kind of circular shape here, you can have a square shape as well.